So here's a project. It's based on wind energy prediction using RNN. For the past few years, reliability on wind power has been increasing rapidly due to its renewable nature. The level of penetration of wind energy in the grid has been increasing rapidly. Reliable short-term wind power forecast plays a crucial role in wind energy conservation systems. To successfully integrate wind energy into the grid at large penetrations of more than 10%, accurate wind predictions are necessary, which is accomplished by load forecasting. Wind power will always have a lot of fluctuation due to variables wind speed, hence the prediction will help manage this variability and avoid balancing problems. The point at which this requires changes from system to system. So the objective of our project here includes estimation of wind power with given parameters like temperature, wind speed, pressure, and then prediction of power generation without the knowledge of weather conditions using the pattern which it has followed in certain period of time. So the methodology of our project includes installation dependencies and loading of the data set, dealing with missing values, that is NaN values with the test statistics, then displaying of the data, then desampling of the data set, then reshaping of when we'll reshape this data set, and then finally we'll execute the neural network model. So the neural network model which we've used there is recurrent neural network, that is RNN, which is a neural network with artificial memory and is recurrent in nature, which means that the same functions is used for every input of the data while output depends on the present input and past output. The inputs are related to each other. The type of RNN we have used here is long short-term memory, LSTM, which is a modified version of RNN. RNN's vanishing gradient problems get solved here, all the while making the storage of memory easier. It trains a model using backpropagation. LSTM has 3 gates, which is for get, input, and output gate.
So wind energy system has been classified into 4 categories due to the difficulty in predictions arised by wind speed variations. So the very short-term prediction is used for real-time grid operations and turbine control, whereas short-term and medium terms are used for load dispatch planning and energy trading. The long-term is beneficial for maintenance schedules. Generally, short-term and long-term predictions are made due to the reliability on predictions and mean absolute error. Coming to the literature review, we did review of 6 base papers on wind power forecasting. The similarities found between them is the use of long short-term memory and GRU methodologies, which have been used in our project. The LSTM and GRU are part of RNN. In most of the papers, short and medium-term predictions are done. The predictions goes well for short time, but as the time increases, the root mean square error increases, and also the prediction depends on the lookbacks. Keeping in mind the above suggestions, we made a model based on short term. Now, coming to the extra assignment given by Sir on electric power load forecasting of a certain household. So electric power forecasting is beneficial as consumption of energy has increased substantially in the past years. By forecasting, it offers means to reduce energy consumption in a household and most importantly, electric bill. Electric forecasting can also help in optimizing the schedule of household appliance. In this project, also we use LSTM for prediction, but for complex model, we brought GRU for multi-layer training. We have used GRU. So GRU, like LSTM, is capable of learning long-term dependencies and is an improved version of RNN. Unlike LSTM, GRU is less complex than LSTM as it has 2 gates, whereas LSTM has 3 gates.
So here is the wind energy prediction Python file which we have created. We start by importing the libraries and loading of the data set. You can see how the data includes power output with weather conditions like temperature, pressure, wind speed, wind direction, etc. And the data starts from 1st January 2007. We got this data from internet sources. We then deal with the NaN values of the data and then divide this data into training data and testing data. So the first model which we have tried has 100 neurons in the first hidden layer, and with mean arithmetic error loss function and Adam optimizer with under 300 epochs. We got the root mean square as 1.228228. All the predictions which we got here are from 29 December 2011. You can see the output graphs which we got for the next 24 hours. And then here's for the next predictions up for the next 48 hours. And then the predictions here are for the next week. And finally, the predictions for the first one. You can see the similarities in the true values and the predicted values in all the graphs. The variance we got here has 0.979 and the mean absolute error has 0.875. In the second model, we have tried that we predicted the power generated with the help of previous data and removed the environmental parameters, wind, speed, temperature, etc. have been removed. The same as we can see here. This method is called as walk forward validation. In this model, we have the number of epochs we have taken as 10. After predicting the values, we can see that this is the output for predicted values for the next 48 hours. We can see that how the predicted values and true values are different after 10 hours. This is because of the variable nature of wind speed. This proves that the model is only applicable for very short time scale.
Yeah, according to the extra assignment given by Sir is to the load forecasting of an household. So first we did all the installments of the libraries, and then we did all the library that we are going to use. That is for deep learning and for all the plotting. So the first we have used is that we merged all the columns for date and time. Then what we did is that we are dealing with the null values. So we use a stat statistics and we have merged all the values and dropped the columns for required. So then we plotted the trend of active power consumption. We can clearly see the seasonal effects and variance across the mean. The same we have done for months here. As you can see, the global active power consumption that has been averaged over the month, and then we have done over the quarter. So next we have to do the resampling of the data because we had 20,75,259 data points. So it is not possible to train such a huge data. So we group all of them to the RE. So the next we have got is 34,589 values. So next we did the LSTM model, which we have designed. So here it is the supervised modeling supervised learning that we are doing with the data. So here first we are doing we are taking all the values in a similar scale from 0 to 1. So it is easy to predict. And so we are splitting the training data and testing data into 70:30 ratio. So here comes the first of our basic model. Here we are using our LSTM models with 100 neurons in the first visible layer. Then it is a dense layer, means that all the neurons are attached with the output layer, and we're having a dropout of 20%. So we are using the mean absolute error to check the functioning. So here's a function. So 20 perks has been used. As you can see, we have got a root mean square error of 0.620, which is okayish, but not true. But we have only used this method to only check whether we are predicting it true or not. So here comes the 24-hour prediction with the above given model. So next, what we have done is increase our efficiency. So we have, like the previous model, we have used 100 neurons. Now then we have only made the changes in the dropout, that is we have changed it to 10%, and the epochs we have increased to 300 epochs. So as you can see, we have all the training data model here, it is like that. So you can see that we have got a root mean square error of 0.604, which is a better improvement from last one. So here we have got a 24-hour prediction, which means the values are nearby same from the actual values. So the same we have got done for the 48 hours, that is for 1 week, 1 month, and 1 year. All the data have been done from the all the x-axis are in hours. So basically all the values are from 20 September 2009. So finally comes the complex model that we have used. So in this we have used is the GRU and the LSTM model. Unlike previous, that is a single layer model. So we have used a complex model, means that it is going to be a multi-layer model. So here we have first used the LSTM model. As you can see the summary, we have used the first layer of 75 neuron, then 30 neuron, another 30. And then we have used a dense layer, means all the neurons are attached with each other. So then we have got the training. So as you can see, which we have got the root mean square error of 0.326, which is half of the previous that we have got achieved. So, but still we want to use the GRU to check whether which LSTM is better in this training or the GRU. So the same model we have applied for GRU model also. The 75 neuron, then 30, 30, and then we have used a dense layer. As you can see, what we have achieved here is 0.262, the root mean square error 0.26, which is the least in above all the cases. So here you can see the graph of all the training and the testing data. As you can see, the training data is nearly same, but the testing data for the GRU test series is more of constant. So as we have gone through, so we have plotted, or we have done all the training through the GRU model, and then we have plotted for 24 hours, 48 hours, and like this. So as you can see, it is rightly predicting all the values are correct. And also all the values are from 20 September 2009, because we have used the last 30% for prediction values. So here comes the first week, and time scale is in hours. So mean that 168, that is 24 into 7 equals to 168. The prediction for 1 week, and it's all in order. So here's the prediction for 1 month, and next we have got for the 1 year. Thank you, sir.